Okay, guys, so we've talked a lot in Fisher projections, which are our linear versions or open chains of our saccharides, our monosaccharides. However, we need to talk about their most stable form. So in reality, we don't really see the open chains very often. They're in an equilibrium with their ring versions or their closed chain versions. So what happens is there's an intramolecular reaction between the carbonyl carbon and the hydroxyl on the end to form a ring, or the last hydroxyl that's chiral to form a ring. So this is like the general scheme for this. So we've been drawing, not in this form, we've been drawing Fisher projections, but we've been drawing straight chain, where what really happens is this oxygen here, maybe we'll do red. This oxygen here, what it does is it attacks this carbonyl carbon and forms a ring. So we have that oxygen there, overall forming a ring. So let's do an example of how to draw this. So, backing up a little bit, the way that what we call these are Haworth structures. So a Fisher projection is the linear form. A Haworth structure is the ring form. So there's a number of steps. It's a lot of what my boss likes to call mental gymnastics. And I'm going to warn you right now, just to be fully open with you, this is my least favorite thing that we're learning this semester. I hate doing this, so we won't be doing it too much, but it's definitely important to understanding the structure of sugars. It's more just converting between the two that is my least favorite part, not necessarily drawing them. Okay, so step one, we have this Fisher projection. So this is D-glucose. So I would like to also point out, this is the general steps for aldohexoses. So it's almost exactly the same for ketohexoses, but you'll see that there's a pretty major difference in what the structure looks like at the end, but we'll get to that in a moment. So our first step is to rotate the Fisher projection 90 degrees. So it's going to go 90 degrees to make the carbonyl go down to the right. Okay, so I'm going to go ahead and number these carbons just so that we keep track very nicely. So I'm going to draw my horizontal line now, and we're going to end with our carbonyl, our aldehyde. 2, 3, 4, 5. So that line's a little too long. Okay, and then I'm going to just add in all of my substituents so that it's the exact same thing, just rotated. So on carbon 2, the OH was to the right, so now it will be down. Number 3, it was up. 4 is down. 5 is down. Add in those hydrogens. Okay, so that's the first step. It's just to rotate the entire molecule clockwise. Step number 2, rotate around the second to last carbon and put the OH on the end. So you see here, my second to last carbon, so carbon number 5 in this case, I need my hydroxide to be in the horizontal line, whereas this hydroxide, I want to move it so that it's in the horizontal line. So in order to do that, I'm going to erase this 5 just to be clear. In order to do that, I'm going to take this oxygen, I want it to go there, so it's going to move to where that carbon was. This carbon is going to move where the hydrogen was, and then the hydrogen is going to move where the hydroxide was. Okay, so now let's just redraw that. So I am going to cheat because I have an iPad right now, and I'm going to duplicate this structure and just erase parts of it. So I'm going to rotate all of this. I'm going to erase these numbers so that they're not in our way. So now we have our OH that we wanted in the horizontal plane. is now going to be where the CH2OH was. So now we'll have CH2OH. And then on the bottom, our hydrogen. So it's still that same enantiomer. We're not changing the enantiomer at all. We're just rotating that carbon to a new orientation. Step 3. So you'll notice that my structure here is the same as the structure here. Label this purple guy. Fold the Fisher projection into a hexagon, putting the OH in the upper right corner. So I will tell you right now, you need to do this in the exact same way every single time. If you put it in a different place, it's going to be super confusing. So I'm going to keep everything vertically as the same as it is, but I'm going to draw out the draw this into a hexane form. So let's do red. Okay, so I'm going to start right here. I'm going to go ahead and put C's for my carbons just to start out so that it's more clear. So I have my carbonyl carbon, and I'm going to draw it like this, where I have my oxygen and my hydrogen. And then I'm going to go down to my next carbon, over to my next carbon, up. We're going in a hexagon. So those are my 6 carbons in a hexagon. I am not going to connect them quite yet. You will see why. I'm going to number, let's go ahead and number these again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same number of carbons in both structures. Now we need to add in the hydroxides and the hydrogens. So on carbon number 2, we had a hydroxide going down. I'm going to put a line going up and a line going down. The hydroxide was going down, hydrogen was going up. So I'm going to keep it that way. Then we have on carbon 3, hydroxide was going up. And then the hydrogen was going down, up, down, up, down. Carbon 6 is a little bit different because it's just CH2OH. We'll get to that in a moment. Carbon number 4, oxygen was down. Carbon number 5, did I label this wrong? No, I didn't. Carbon number 5, oh, I'm sorry, that's what I did wrong, is that this carbon number 6 is actually going up now, right? Because our horizontal line is going to be what is our cyclohexane. So I drew this wrong. That is why I was confused. We're going to put our oxygen that we had in our horizontal line is going to be the end of our hexagon words. We got to move down. I drew this too big. So carbon number 5, we have the hydrogen going down, and then CH2OH, which was carbon 6 here. Okay, so just for clarification, we keep that whole horizontal line is going to be what is in our hexagon. So we go down and around. Our last point of our hexagon in the upper right-hand corner is going to be our hydroxide, so that our carbon 6 is actually going to be sticking up. So the parts that are up are going to stay up. The parts that are down are going to stay down. You don't have to draw in the carbons per se. So you'll see in this next structure that the carbons are drawn in, but later we're going to delete them out. So our last one, you'll notice that the one I drew in red and this one in the box are the same. And the last one, we're going to form the ring. So let's go ahead and add our purple oxygen back in. And what we're going to do is we're going to connect, let's do orange. We're going to connect this oxygen to this carbon. And then this double bond, we're going to get rid of the double bond. It'll form a hydroxide. Those electrons are going on to the oxygen. And then this hydrogen here is actually going to jump ship and go on to the oxygen. So in reality, we're going to draw that the opposite way. the oxygen is going to steal the hydrogen off of that, the purple oxygen. Okay, so to form that ring, what this looks like, I'm going to draw my hexagon. I'll leave a space right there because that's where my oxygen is going to be. Let's go ahead and draw in all of our lines going up and down, just like this. Fill in everything but what's going on. Let's fill in the rest of it. So we have a hydrogen going up, oxygen going down, hydrogen going down, oxygen going up. Okay, so now carbon number 1, the carbonyl carbon, is where we're going to mix things up a little bit. Actually, I'm even going to erase this and make this orange to show we made this bond here. Then our alcohol is either going to be going down or going up. So we don't have any particular way that we know that it's going, right? Because the when you do this, when it attacks that carbonyl, it can attack either side of it, and therefore you can have the hydroxide going up or down. And then you fill in, so this, let's go ahead and change this H to blue to show that it was that one that we stole. So the carbonyl is going to turn into an alcohol. This is called, nope, that's fine. So when we do this, you'll see step 5 is to draw both the alpha and beta isomers. So I'm going to copy this structure and put them down here. I'm going to put two of them to show you the difference between the two structures. So I showed that the oxygen goes down when we do this. Actually, we're going to switch these colors around real quick so that everything's just red except for this alcohol here. I'm gonna erase this hydrogen. There we go. So if I have this basic structure here, when that ring closes, it's going to form either the hydroxide on the bottom or on the top. So if the hydroxide goes to the bottom, like this, and the hydrogen's on top, this is called the alpha isomer. And then if the hydroxide goes to the top instead of the bottom, this is called the beta isomer. So you can have an equilibrium between these two. So the process of converting back and forth between the alpha and beta isomer. So alpha, all we're doing is when we make that ring, there's a choice whether the carbonyl carbon goes up or down. And if it goes down, it's alpha. If it goes up, it's beta. There's also, if you have, there's an equilibrium in between these. So that bond that we just formed to make the ring is pretty weak. And what can happen is this glucose here. So we're going to highlight that it's the alpha glucose because we have the alpha isomer since it's going down. We can then break it into the linear form again, and then reclose that ring. And now we can reclose it the opposite direction into the beta isomer. So specifically for glucose, it's not a perfect equilibrium in that it's not 50-50, but there's an equilibrium of about 36% to 64%. So particularly glucose likes to favor the beta form of glucose. So the process that converts back and forth between alpha and beta isomers is called mutarotation.